What good is a miracle molecule if it degrades into total uselessness, or worse, becomes actually dangerous before it even enters your body? The reality is, the environment all around us, the water, the oxygen, the light, the temperature changes, it is incredibly hostile to complex chemical structures. Protecting these vulnerable molecules is the true art and science of pharmaceutical development. Here's our roadmap for this explainer. We're going to cover the preformulation mission, chemical threats to stability, the danger of racemization, the BCS classification system, designing stable dosage forms, and finally some high-yield takeaways. Okay, let's start with Section 1, the preformulation mission, which is really the foundation of formulation development. So what exactly is preformulation? Well, it's the systematic evaluation of a drug's physical and chemical properties. You can almost think of it as a comprehensive interrogation of a molecule. Long before we ever try to compress a powder into a tablet or dissolve it into a syrup, we absolutely have to understand its baseline behaviors. This systematic evaluation is the absolute critical first step to guarantee a drug is going to be stable on the pharmacy shelf, completely safe for the patient, and highly effective once it's actually administered. Moving on to Section 2, chemical threats to stability. Let's meet the molecular villains. The most common and frankly relentless threat out there is hydrolysis. Basically, this is a reaction where water literally cleaves a molecule's chemical bonds right apart. If a drug has readily hydrolyzable functional groups, things like esters or amides, even just ambient moisture in the air can rip the molecule to pieces, often degrading it into totally ineffective carboxylic acids or alcohols. Take aspirin, for example, known chemically as acetylsalicylic acid. If you don't strictly protect it from moisture, water attacks the ester bond. It rapidly breaks down into salicylic acid and acetic acid. And not only does this destroy the active drug, making it way less effective, but you can actually smell this degradation. When an old bottle of aspirin starts to smell faintly like vinegar, yeah, that is literally the acetic acid being released right in front of you. Now, because water attacks salts, acids, and bases very differently, formulation scientists can't just guess how stable a drug is going to be. They have to perform rigorous stress testing. They intentionally try to destroy the compound by refluxing it in harsh acidic conditions, like 0.1 normal HCl, and highly alkaline conditions for 8 to 12 hours, just to identify its exact breaking points. And the real-world consequences of understanding this are massive. Let's look at local anesthetics. Procaine is an ester derivative, which makes it highly susceptible to hydrolysis and therefore very short-acting in the body. But by designing lidocaine as an amide derivative, it resists hydrolysis much better, giving us a reliable, long-acting anesthetic. We also see this exact same principle with beta-lactam antibiotics, like amoxicillin. Because they are so vulnerable to hydrolysis in liquid form, they're manufactured and shipped as dry powders that you only mix with water immediately before injection. But okay, once we conquer water, we immediately have to face air and light. Oxidation involves a molecule losing electrons. This is often triggered by atmospheric oxygen, free radicals, or just exposure to light and higher temperatures. Formulators fight this using dark packaging, strict temperature controls, and adding antioxidants. On the flip side, we have reduction, the gain of electrons, which can completely change a drug's chemical identity and how it behaves inside the human body. Reduction can actually be a bit of a double-edged sword, depending entirely on the molecule. In the liver, reductase enzymes catalyze reduction reactions that actually activate the sedative chloral hydrate, turning it into its active form, trichloroethanol. But that exact same reduction process can dangerously inactivate critical drugs, like the blood thinner warfarin, by transforming a crucial ketone group into a hydroxyl group. All right, Section 3, the danger of racemization. The mirror image threat. Have you ever thought about how your left and right hands are exact mirror images, but you can't superimpose them? Well, chiral molecules are exactly like that. They contain the exact same atoms, connected in the exact same order, but they are non-superimposable mirror images of each other. During preformulation, a process called racemization can actually convert a pure, optically active compound into a 50-50 mix of both versions, called enantiomers. The big problem here, even though they look identical on paper, they fit into the human body's complex biological receptors in completely different ways. A historical lack of knowledge about this chiral selectivity led to one of the darkest moments in all of medical history, the thalidomide tragedy. Thalidomide was distributed as a racemic mixture.
Preformulation scientists at the time didn't realize that while the R enantiomer was a highly effective sedative for pregnant women, its mirror image, the S enantiomer, was a devastating teratogen that caused severe birth defects. Today, rigorous preformulation ensures we isolate and stabilize single preferred enantiomers. That's why, today, we prescribe specifically escitalopram instead of the older racemic citalopram mixture. Section 4. The BCS classification system. Mapping out the strategy.
The Biopharmaceutical Classification System, or BCS, categorizes drugs based on two absolute deal breakers for oral absorption: their aqueous solubility and their permeability across intestinal membranes. At one extreme, you've got Class 1 drugs like paracetamol. High solubility, high permeability. These are a formulator's dream because they absorb so easily. At the exact opposite extreme are Class 4 drugs like bifenozole. Low solubility, low permeability. These present a massive challenge and usually lead to really variable and poor bioavailability in the patient. Using the BCS quadrant allows scientists to predict how a drug will act inside the body based purely on simple lab tests. They look closely at things like a drug's partition coefficient, its lipophilicity, which dictates how well it can cross cell membranes. So if a drug falls into Class 2, low solubility but high permeability, they know they might need to shrink the particle size. If it's Class 3, high solubility but low permeability, they might need to add permeability enhancers. It's essentially a predictive roadmap for drug delivery. Which brings us to Section 5, Designing Stable Dosage Forms, Building the Shield. Choosing the exact solid form of a drug isn't arbitrary. It requires meticulously mapping out its chemical properties. We have to analyze the drug's pKa to understand its ionization state across all the different pH levels of the GI tract. We establish its pH solubility profile, and all of this feeds into a rigorous stability analysis. The goal is to ensure the selected solid state, which often means choosing a highly specific, stable crystal polymorph over an unpredictable amorphous form, will survive the harsh manufacturing process and stay stable on the pharmacy shelf. To successfully manufacture a final dosage form, scientists essentially have to act as master balancers. They balance physical traits, like hygroscopicity, which is a powder's tendency to absorb moisture from the air, against chemical traits. They run strict drug-excipient compatibility tests, so the active ingredient doesn't accidentally react with its own packaging or filler materials. And they definitely have to factor in mechanical traits, like compressibility. Simply put, if a powder doesn't flow well through the machinery, you literally cannot manufacture millions of perfectly dosed tablets.